we're going to finish the implementations of the domains today. So you've seen a lot already last time, mostly the sparse set implementation. And that, that implementation had 3 different components: 2 arrays, index and value, and then an int, capturing the size of the set. The array value is interesting. All the values initially in the domain of the in the set are inside that array. And the size is telling you which one are really in the array at this particular point and which one have been removed. The array index, as you remember, is telling you the position of every one of the value inside the array value. All right. So one of the things that I told you that was extremely important is the ability to undo the changes that you had done. And so if we want to undo the fact that we had removed the value 4, we can simply move the size here back there. And now 4 is again inside the array, although it's not in the position that it was initially. But that's not a big deal, right? So the fact is that all the values are in the set, and we can find out that they are in the set, and we can find out where they are. All right? So now, how do we implement this in Java? Okay, so what I'm going to show you is that we're going to implement the domain and the sparse set such that they can be saved and restored. That's the key asset that we need to have. We need the ability to save and restore this particular sparse set and the domains, essentially. So to do that, we'll have an abstraction which is a state manager and state integers. So there are some integers that we need to say, hey, we want them to be safe because I need to restore them. The size, integers that we were using in the previous slide is like that. We want to restore its value if we go back to a previous state. Okay. So the key functionalities of the state manager is that the state manager is going to keep track of all these entities that need to be restored, and it can save them in a state, and later on it can restore that state. Okay. Now, what do we have to do to save all the domains? The only thing that we need to do is to actually save the sizes of the domain. Every domain we save the size, and then we can restore them in constant time. And that's really, really useful. Now, we're going to do a little bit more than that. We're going to also save the min and the max, because that avoids us to do recomputing, the min and the max from time to time. But roughly speaking, the only thing that you really need to save is the sizes of every one of the domains. So let's look at a little bit of the code here. So this is the constructor of and the data that is inside my sparse set. So I have the array value, as you expect. I have the array index. I have size. I also keep the min and the max to speed that up. I will tell you what this is later on. And n is the initial size, so that my array is going from 0 to n minus 1. That's the size of the domain. All right, and so I'm initializing the size, the min and the max at the beginning, creating these arrays and initializing. That's my basic construction of my sparse set initially. Now there are 2 things here which are actually interesting. Is that I'm using a state manager and a state int for the size, the min and the max. I'm not using an int, like for instance the size of the domain initially, the size of the domain initially, or the offset that I will talk about later. Why? Because those don't need to be a restore. I don't change them, or they can stay the same. I'm also not trying to save these 2 arrays. They don't need to be saved. They can stay the way they are even when I go back, when I undo some of the changes. But these guys are state variables here. I want them to be saved. If I'm about to make a change, I want to be able to restore them. And that's why I'm using this state manager. So a state int is actually extremely simple. It's something that actually save one int, an integer there, and I can set the value of that integer and get that value. So it's just an object encapsulating an int, nothing interesting. The state manager is more interesting. It allows you to create these state ints, so it acts as a factory for creating these guys, and that's what you see here. When I have the size, I'm asking the state manager to make me a state int and give it the value n, which my initial size of the array. But it can also do 2 things: save the state and restore a state. Okay? Now, how do we save the domains? The only thing that we have to do is to save all the sizes and the min and the max of every one of the domain. How do we restore the set of domains? We just restore the size, the min, and the max of every one of the domain. Very, very simple. Visually, this is what the state manager does. The state manager, because you create the object through him, knows everything that has a state that needs to be restored if we modify it, right? And so when the state manager wants to save a state of the computation of the domains, he's going to create this box there, and he's going to take all the state variable, the state int, and put them in that box with their current value. It's going to copy all these states and put them in the box. And when it needs to restore them, it's going to take all these values which are in that box and restore them to this particular state variable. So you'll see that in more detail later on, but this is how we construct the domain, and this is how we'll be able to save and restore these domains, right? This is pretty cool, right? All right, so let me show you what the index is used for. If my base is not 0 to n-1, if my domain is not 0 to is not 0, so the domain is not from 0 to n-1. If it, let's say, from 10 to 20, I'm going to use an offset of 10. And that offset is going to tell me, hey, I'm going to represent my values from 0 to 11, from 0 to 10, sorry. But I have an offset of 10 that I have to add to every element if I want to enumerate all the values in the domain. Or if I want to query what they are, this offset is going to be very, very useful. So I can create a domain which says I have n values, and they start at this particular offset. So it's going to be 0, it's going to be offset plus 1, offset plus 2, and so on and so forth. All right? And so when you do this, there is very little that you need to do. The only thing that you will do when you get a value is use the offset to actually get the actual value when it's rescaled in between 0 and n-1, when n is the size of the domain initially. So this is the entire, no, not the entire, but a big chunk of the code of the state sparse set representation. And I'm going to go with you to actually two of these methods. The first one is the contain method. I have a value val, let's say 15, and I want to see if it's inside the array. So the first thing that I do is that I remove the offset. So if it's 15 and my array was 10 to 20, it's going to become 5. And now I'm going to look into my representation, the values that I have, which are between 0 and n-1, and that's where I'm going to look into, right? So I have the value 5. Now I look if this is smaller than 0 or greater than n. If this is the case, the value greater or equal to n, then the value is not in the domain. I return false. Otherwise, I do what I told you before, right? I look at the index of this value, and if it's smaller than the size, okay, the size is here. This is the size of the sparse set. Then, if it's smaller than the size, it's inside the set. Otherwise, it's not. Okay, pretty cool, right? Now, removing a value is also interesting. The first thing that you do is you test if the value is inside the domain. If it's not inside the domain, you don't have to remove it. Otherwise, you remove the offset, obviously. You take the size of the set again. You exchange the position of that particular value and the last value in the array. So that's why you collect the size here. Then you decrement the size. So the size, boom, you remove the last value, which is the value that you just swapped. And then this method here is actually updating the min and the max. I won't show you the details of this, but this is what it does. Exchanging position is easy. That's the kind of things that I've shown you before. You store the value, you store the indices, and then you swap them. So that's what we need to do for actually removing a particular value from the sparse set. Okay, cool. Now, the domain implementation, you're going to see, once we have done this, it's going to be really simple. But I need to tell you a little bit what it does. So mostly what the domain is going to do is delegate all these operations to the sparse set. If I want a sparse set domain, what I'm going to do is delegate most of the thing to the state sparse set. Okay, but the domain has also some very important features, and we discussed them when we were discussing the fixed point implementation, right? So it has to inform the outside world of various things. And the way to think about the outside world here is really the variable and the constraint propagation. So, for instance, the domain is to say, hey, I'm becoming empty, or, my minimum and maximum value have been removed, or, I lost an element, or, I have a single value left, And so that's what the domain is to be able to tell the outside world. So the domain is to update the set, but it has also be able to tell the outside world what is happening to it, okay? And so this is implemented through a listener. which is a nice abstraction when you do a complex implementations. And I'm going to show you that again. So, right, so this is the interface of the domain. And I conveniently omitted this domain listener before because I didn't want to talk about it, right? So now is the time to talk about it. So what is this listener doing? This is actually an object which an interface, if you want, that responds to these methods there. It can tell the world that it's empty, or that it has a single value, or that it has changed. The value has been removed from the set, or that its minimum or maximum value have changed. So think of this is essentially an object that you pass to the domain such that the domain can inform you what is happening to it. All right? And so once you have this listener there, this is what you do when you implement a sparse set domain. So a sparse set domain is going to be very easy to implement. You're going to use a domain, which is the state sparse set. So that's basically the set that you're representing. And most of the time, what you're going to do when you want to implement min, max, and size is just delegating to this sparse set. If you want to find the min of this domain, you ask the sparse set, hey, what's your min? Or hey, what's your max? What's your size? Do you have this value or not? The only place where you have something which is really interesting is in the methods that are removing all but, below, and above. And I'm going to show you one here. So this is the method for removing. And so essentially the key point here that you have to do is first you test if the value is inside the domain, because if it's not in the domain, then you can throw it away. And then you're going to remove it. But all the rest that you see there, it's just informing what happens to the rest of the world, right? So you have the domain listener, and you're going to tell the domain listener that, hey, I'm becoming empty, or, I have changed, or my max or my min has changed, or, I have single values left. That's what you are doing. So in a sense, you are basically, testing if the value is there, you're removing it. If the domain is 0, you tell the domain listener, hey, tell the world that I'm empty, and if it's not empty, but a value has been removed, you're going to say, hey, I've changed, my domain has changed. This is very important because that tells the constraint propagation that all the variables which have this, all the constraints which contain these variables whose domain we are modifying right now have to be propagated again. Changing the min and the max is very important as well, telling the system, because some of the constraints, they only react when you change the min and the max. So we have seen that, in previous video, the way you propagate linear inequalities by looking at the min and the max only, nothing else, right? So this is why you tell the world, hey, my max has changed, oh, my min has changed, right? So that's what you do here. So at this point, so what you have seen is essentially the implementations of a domain using a sparse set, a state sparse set. You know essentially how to implement this sparse set. You know that some of the things have to be preserved, they have state, and then you know that you can actually tell the outside world how your domain is moving through this domain listener. So at this point we have this domain, we can use them, and we're going to use them for implementing variables in the next video. So stay with us, it's going to be interesting again. We are going to move to another level here inside the implementation. It's going to get even more interesting.